Now that you know a little bit about stoichiometry, I want to show you how to use the conversions to convert from one chemical to another while you're doing these problems. I'm just going to work a bunch of examples with you in this set of slides, and hopefully it'll give you a better understanding. So let's get started. Now remember that you have to use the balanced equation when you look at a stoichiometry problem. When we look at this equation, it's the synthesis of water, we don't talk about 2 grams of hydrogen and 1 gram of oxygen. Remember, a chemist talks about the amounts in terms of moles. So you're going to be using that mole ratio from these coefficients. But with grams, that's going to be an extra conversion step. There's a pattern that a lot of these problems follow, and here it is. Generally, you will start with the mass of one compound, or grams of a compound. You'll use its molar mass from the periodic table to convert that to moles. Once you have moles, you're going to use the mole ratio. That's the coefficients and the ratio from the balanced equation. You convert to moles of a different chemical, and once you have moles of that chemical, you use its molar mass to convert back to grams. So a lot of times chemists refer to this as grams to moles to moles to grams, or a mass-mass problem. For this first example, let's simply look at the pattern that we would need to take, the path. Let's don't work it out, let's just think about the steps in that pathway. If we had this reaction for the synthesis of water, if we started with 2 moles of water, how could we get to grams of water? Well, I think because this is water and this is water, this is going to be a mole A to gram A problem. We're not changing the chemical C, we're staying with water. So it's just a one-step conversion using molar mass. What about the second one? If we were trying to find the moles of oxygen required for 36 grams of hydrogen to react. Now those are 2 different chemicals, so I think I'm starting with grams of hydrogen, which is A. I would have to convert this to moles first. Once I have moles of hydrogen, I would have to convert it to moles of oxygen. That's the mole ratio step. And that's where I would stop. That's what this question asks for. So this is a 2-step conversion. And finally, I need to find out in this question the grams of hydrogen produced, grams of water produced from 6 grams of oxygen. Because they're different chemicals, I'm going to have to start with grams of oxygen. I can't go straight to water there, so I'm going to have to use the periodic table to go to moles of oxygen. Then I'll use the mole ratio to convert moles of water. And finally, I'll use the molar mass to go to grams of water. So this is actually a 3-step conversion. This is the full pathway that I showed you on that previous slide. Let's use this pathway to work out some problems. Here's my balanced equation at the top. I'm given that. The first question asks us to figure out how many moles of water can we make using 0.5 moles of NH3. Okay, so I'm going to start with my given, 0.5 moles of NH3. And I want you to write the unit and the chemical down here. It'll help you keep track of where you are in that pathway. Since I already have moles, I need moles of NH3 to cancel, and I'm going to convert it to water. I'm going to do moles of water. Moles of water from moles of NH3, remember, is just a 1-step conversion. So I'm going to get these numbers from the coefficients in the balanced equation. There's a 6 here in front of water, and there's a 4 here in front of NH3. So moles NH3 cancels. I need to use my calculator here. I'm going to multiply straight across the top. 0.5 times 6, divide by 4, and you get 0.75 moles. That's the number and the unit, and I also want to put that it's moles of water. What that means is if all 0.5 moles of NH3 react, I will make 0.75 moles of water. Let's do this next one. What mass of NH3? Now that's going to be grams. And I'm starting with 1.5 moles of nitrogen monoxide. So I have moles, and I need to go to grams of a different chemical. This is going to be a two-step problem. The first thing I have to do is convert the moles of NO to moles of NH3. That's the mole ratio. So moles of NO is going to cancel out down here on the bottom, and from the balanced equation there's a coefficient of 4. The NH3 also has a coefficient of 4. Then I'm going to take the moles of NH3 and I'm going to convert it to grams. Now I know from an older chapter that I need the periodic table. 1 mole of NH3 has a molar mass of 17 grams. So those moles cancel out. Grab your calculator and do the math. 1.5 times 4 times 17, and then divide by 4 on the bottom, don't forget that, and you get 26 grams of NH3. So we converted from moles of NO to grams of NH3, and we did 2 conversions here. And finally, this one asks us to go to grams of nitrogen monoxide from grams of a different chemical, NH3. Grams to grams is that whole path, so this is a 3-step problem. I'm going to start with my given, 120 grams of NH3. Remember, write down the unit and the compound. I need grams of NH3 to cancel, and I'm going to have 1 mole NH3 on top. This is just a gram to mole conversion. Using the periodic table, the molar mass of NH3 is 17 grams. So that cancels out. Now I've got moles of NH3 that I need to cancel out. So I'm going to put moles NH3 on the bottom. I'm trying to find nitrogen monoxide, so I'm going to put that chemical on top. The ratio from the balanced equation is 4 to 4. And those units cancel out. And the final conversion step is to convert 1 mole of nitrogen monoxide to grams of nitrogen monoxide. When I get the molar mass from the periodic table for NO, that should be 30. And now all I need to do is the math in the calculator. Multiply straight across and then divide by all the numbers on the bottom. And I got 212 grams of NO. Let me squeeze that in here. So that's a full 3-step conversion. I want you to notice that in this first conversion, I only used molar mass from the periodic table. And in the third conversion, I only used molar mass from the periodic table. The only place you use the balanced equation is in this middle step when you have moles on top and moles on bottom. Keep that in mind when you're looking at your pathway. Alright, let's try another one. In this equation, we are doing a combustion reaction. We're going to start with 400 grams of butane, and we're going to figure out how many grams of oxygen that will produce. That's going to be a 3-step conversion. So write down your given first, 400 grams of C4H10. Remember, in the first step, I'm going to use the periodic table. So 1 mole of C4H10 has a mass of, we need to go to the periodic table and add that all together. Carbon is 12, hydrogen's 1, so when you multiply all that out, you're going to get 58 grams. The middle step is where we're going to use the balanced equation, because I'm going to have moles of butane on the bottom, and I'm going to have moles of oxygen on the top. The ratio here, if you look at the equation, is 13 to 2. For every 13 moles of oxygen, you need 2 moles of butane. And then the third step, remember, is just a gram step. I'm going to find the grams of oxygen from the periodic table, 16 times 2 is 32 grams. So let's cancel out all those units, and we'll do the math in the calculator. 400 times 13 times 32, divide by 58, and divide by 2. And I'm going to get as an answer here 1,434 grams of oxygen. It's quite a large number, but we're starting with 400 grams of butane, which is also a pretty big amount, so don't let that bother you. Now the second question is something we've not looked at yet. What volume of carbon dioxide is formed? Remember that volume is the 22.4 liter conversion that we learned in one of the earlier chapters. So we're going to make use of that conversion in this problem. Now let's start with our 400 grams of butane again. The first part of this problem is going to be the same conversion that we used up top. I know that 1 mole of butane, it has a molar mass of 58 grams. So you see how that looks exactly the same. But in this middle step, while I am going to get rid of the moles of butane on the bottom, I'm looking for a different chemical. The first time I was looking for oxygen. This time I'm looking for carbon dioxide. So I'm going to put moles of CO2 there. And the coefficient with CO2 in the equation is 8. Okay, so far I've converted grams to moles and moles to moles. Now here's where the 22.4 liters comes in. I know that at standard temperature and pressure, 1 mole of any gas occupies 22.4 liters. So that's the hint why I gave that to you. Okay? So now all we need is our calculator. 400 times 8 times 22.4. And I'm going to divide that by 58 and divide it by 2. And you will get 618. The units here are liters of carbon dioxide. So I wanted to work this one out just so you could see that we do still have that 22.4 liter conversion available to us when we're working with gases in these stoichiometry problems. Alright, the next example, we're starting with moles of HCl, and we're going to grams of aluminum hydroxide. So the pathway here is we want to convert moles of HCl to moles of aluminum hydroxide, and then I need to convert that to grams of aluminum hydroxide. When I think about this pathway then, this is going to be a two-step problem. I'm going to write down my given first. 5.3 moles of hydrochloric acid. I need to convert moles of HCl to moles of aluminum hydroxide. So that's going to be a mole ratio conversion. I'm going to put moles of AlOH3 on top, and I'm going to put the moles of HCl on bottom. The ratio from the balanced equation is 1 to 3. Now that 1 for the aluminum hydroxide is understood there. Don't forget that. Moles of HCl is going to cancel out, and I'm going to have moles of aluminum hydroxide. And then I need to convert to grams. When I have a gram as part of the conversion, all I need to do is get the molar mass of this compound from the periodic table. So you need to add up 1 aluminum, 3 oxygens, and 3 hydrogens. If I've done my math correctly, that's 78 grams. So that cancels there with those units. When you do the math, it's just simple multiplication and division. 5.3 times 78, and then divide by 3. The answer here comes out to be 138 grams. But now it's aluminum hydroxide. So a chemist would use this to know if he had this much hydrochloric acid to start with, 5.3 moles, he would need to measure out 138 grams of aluminum hydroxide for all of these reactants to be used up. It prevents a chemist from wasting materials or from not using enough to begin with. Alright, last example. This one looks a little bit different too. But again, I gave it to you because I want to remind you about some older conversions that you still have available to you. This question starts with formula units, which are like particles. Now, we've not done one of these problems in this unit, but what we can do is work from particles of calcium chlorate, I'm going to call that A. We can convert to moles of A using Avogadro's number. Once we have moles of A, we're going to convert to moles of a different chemical, which is going to be our oxygen. And I need to get the mass of oxygen, which is going to be in grams. This is going to be a three-step conversion. So let's start out with the 3.2 times 10 to the 23rd formula units. I know that in 1 mole of calcium chlorate, there should be 6.02 times 10 to the 23rd formula units. Remember, Avogadro's number is standard. So the formula units are going to cancel. That's this first step. My next step is to convert moles of calcium chlorate to moles of oxygen. So I'm going to put moles of calcium chlorate on the bottom so that it cancels. And I need moles of oxygen on top. You get the mole ratio from the balanced equation, and for this equation it is 3:1. Last step, we're going to go from moles of oxygen to grams of oxygen. I only need the periodic table. 1 mole of oxygen has a molar mass of 32 grams. So my moles cancel out, and then I need to do the math. Be careful here when you're dividing by Avogadro's number. You may need to put that in parentheses. So I'll do that for you just to make sure that you get that right. So 3.2 times 10 to the 23rd times 3 times 32, divide by 6.02 times 10 to the 23rd. What you should get here is 51 grams of oxygen. Make sure you check your calculator and make sure that there's not an exponent at the end of your calculator answer. If there is, you've entered this division incorrectly. So we need to work on that with your calculator. You've set it all up right, but sometimes remember putting that number in with scientific notation is a pain and kind of tricky. So if you got the exponent, try and rework it and put this number in parentheses and see if that helps. But you should get 51 grams of oxygen. So really this stoichiometry pathway has multiple parts. We generally start with grams, but you can start with particles or with liters, and we generally end with grams, but also you could end with particles or with liters. So keep practicing. I know these are hard and they do take some time, but practice makes perfect, and I'll see you next time.